Hey guys, what's up? I hope everyone's having a great day. Today, obviously, I'm working from home, which is good. Excited that you guys are coming back, right? We get to see a couple more of you guys tomorrow and the next day. But today, we're just going to be kind of going over the test review, right? So, we're going to spend some time going over the solutions here, real quick. And let me just get this going here. Okay, so starting with number one, right? We're evaluating the logarithms here, right? And when we think of logarithms, right, what we have to get used to is that transformation, right? So log base 4 of 4 is really saying 4 raised to the what power, or what in this case we'll call it the x power, is equal to 4, right? So 4 raised to the x power equals 4. X in this case would have to be 1, right? Because 4 raised to the 1 power is 4. And we can say the same thing with number 2, right? This is saying 6 to the what power is 1 over 36. Because it's a fraction, we know it's going to have to be negative. And then 6 squared is 36, so we have x equals negative 2. Right? For number 3, we have, and I know it's kind of hard to see, but this is log base 5, right? So this is saying 5 raised to the what power is 1. Well, that would just be 0, because anything raised to the 0 power is 1. Number 4 gets a little more tricky, right? It's 25 raised to the what power equals 125. Well, if we think about 25 and 125, they're pretty friendly numbers, right? Because 25 is just 5 squared. So we can write 25 raised to the x power as 5 raised to the 2x. Right? And then 125, well, that's just 5 cubed. Since they have the same base, we can just go 2x equals 3, and we end up getting x equals 3 halves. Right? Number 5 is asking 2 raised to the what power is 64? Well, that's just 2 raised to the 6th power. Number 6 is saying 7 raised to the what power is 7 to the 4th? Well, obviously, it would just be 4. Right? 7 raised to the 4th power is equal to 7 raised to the 4th power. All right, let's keep going. Let's talk about graphing here. Right? So remember, when we're talking about graphing, it's important to note a couple things, right? We're going to need to know the domain and range. We need to know the vertical asymptotes, and we need to know the end behaviors, right? And then also to make an accurate graph, we need at least 3 points. So, right, so just looking at our equation here, we have f of x is equal to 3 plus log base 3 of x minus 2. Right, the first thing we should try to do is figure out, okay, what are my transformations, right? So if I look at this plus 3 here, I should know just by looking at this, right? This is going to take my value and bump it up by 3, right? Plus 3. And then here, I have my x values. And what we got to remember is whatever's happening to the x, we should think opposite, right? So this is x minus 2, so it's going to go to the right 2, right? So the domain in this case, we determine that because we know in the logarithm, we can't have a 0 or a negative. Well, what would give us a 0? If we plugged in 2, we'd get a 0 inside of the logarithm. So we know the domain starts at 2. And it's going to go till infinity. Right? Then range for logarithm functions, they're always negative infinity to infinity. Right? Which means our vertical asymptote is going to be at x equals 2, because we can never have a 2 in here. So we can get really close to it, but we can never touch it. So the vertical asymptote is at x equals 2. Right? Then what we can do is we can kind of flip around our equation so that we can solve for our points. Right? The first thing I changed the f of x to y, and then I subtracted 3. So I got this y minus 3 equals log base 3 of x minus 2. And this is saying 3 raised to the y minus 2 power is equal to x minus 2, right? Just like the transformations we did up here. And we get, once we solve for x, we get x equals 3 raised to the y minus 3 plus 2. We can just plug in our values, right? And what we want to do is we want to take this transformation, this plus 3, and we're going to kind of make that our first y value, right? So since it's going up 3, I want to solve what is x when y equals 3. Then I want one below that and one above that. because that'll get me a really good representation of the graph, right? And again, every logarithm graph before transformations has a point at 1, 0. Right, so really we're finding that point after it's transformed. Well, it goes up 1, 2, 3, and right 1, 2. Right, that's this 3, 3 right here. Right, so that's why this is the important one to find. Right, and then once we plug in the values, right, 2 we can plug in 2 minus 3, you can solve that. 4 we can plug in 4 minus 3, right, we can solve that, and that'll get us the rest of our points. Number 8 is the same thing, right? We find that the transformation, this is a -2, right? Which means it's going to go down 2. And then because it's x plus 3, we're going to go to the left 3. Right? If we plug in a -3, we'll get a 0 in the logarithm, which we don't want. So that's the end of our domain. Right? -3 to infinity. Range, same thing, -infinity to infinity. So our vertical asymptote then is at -3. Right, just like it was at 2 here. We can't plug in -3, so there's going to be a vertical asymptote there. Right, then same thing here, we can just transform it just like we did over here. And then because of this -2, I'm going to find y at -2, y at -1, and then y at -3, and find the corresponding x values. Right, and again, we just plug that in, right? -1, we'll plug that in. We get 4 raised to the -1 plus 2 minus 3. Right? Then same thing with -2 and -3. Right? Let's keep going. So let's expand some logarithms. So here we're starting with this log base 5 of 2 times the 4th root of x all over 25. And what we can do here is we see this fraction line, right, this division problem, and we know, oh, we can split that up into 2 logs that are being subtracted, right? Then we see this 2 times the 4th root of x. Well, that's a multiplication problem right there. That's 2 times the 4th root of x, so we can split that up into an addition problem. So we get log base 5 of 2 plus log base 5 of x, and remember, if it's the 4th root of x, we can just say x to the 1/4. And then what we did here, this log base 5 of 25, well, that's just saying 5 raised to what power is 25? And that would just be 2, right? So we can just write that as 2. So our final answer then, because once we remember the property here we would use, is we can take this exponent and pull it out in front of our logarithm, right? So we have log base 5 of 2 plus 1/4 log base 5 of x minus 2. All right, important thing to know here, make sure we're always writing the log base, because remember, they have to stay the same, right? Unless we're going to solve the logarithm, which we did here. Right here we can see this is just log base 2 of 16 times x to the 5th times y cubed. Well, that's just 3 numbers being multiplied, so we can split that up into 3 different terms being added together, right? Here we have log base 2 of 16 plus the log base 2 of x to the 5th plus log base 2 of y to the 3rd. Right? Then we're going to use the properties that we know for exponents. We're going to take these exponents and pull them to the front of the problem, right? And then log base 2 of 16, if we think about that, well, 2 raised to the what power is 16? That would just be 2 to the 4th, right? So we have 4 here. We pulled the 5 out, so we have 5 log base 2 of x. We pulled the 3 out, so we have 3 log base 2 of y. All right, and now let's do some condensing. Here, we're kind of doing the exact opposite of what we did before, right? So this 5 log base 3 of m, what we're going to do is we're going to take this number that's outside and we're going to make it the exponent, right? So this becomes log base 3 of m to the 5th. We can do that same thing with this minus 4 log base 3 of k and make it log base 3 of k raised to the 4th power. Right, then we have this 1/2 out here. Well, we can just change that to log base 3 of d to the 1/2. right? Again, we're just taking the coefficient outside and we're making that the exponent. Then I see this subtraction problem here. I have two logs being subtracted, which means I can just make them a division problem, right? A quotient. So I have log base 3 of m to the 5th all over k to the 4th. And then I see this plus log base 3 of d to the 1/2, which just means I can multiply these two values together, right? And when you multiply them together, it becomes log base 3 m to the 5th of square root of d, which is just d to the 1/2, all over that k to the 4th. All right, so I just multiplied this d to the 1/2 times this m to the 5 over k to the 4th. All right, number 12. Number 12. Now, this one's a little different because it starts with 3, right? And we can't really combine 3 when it's being added to a log. So what we have to do is we have to change 3 to be a logarithm with the same base as the other ones, right? So here we have log base 4, here we have log base 4. So we got to think, okay, log base 4 of what is equal to 3? Well, I know 4 raised to the 3rd power, that's just 64, right? So we can say 3 is the same thing as log base 4 of 64. And now it becomes a little bit easier to combine them because they all have the same base. Right, this 12 log base 4 of d, we're going to take that coefficient and make it the exponent. This becomes log base 4 of d to the 12, and then minus log base 4 of w squared. All right, then we see this addition problem. We know we can multiply the terms inside, and it becomes log base 4 of 64 times d to the 12, minus log base 4 of w squared. The subtraction just becomes a quotient, right? A division problem. So we have log base 4 of 64 d to the 12th all over w squared. So moving on. Number 13, we're given these three values here. Log base 9 of m equals negative 1.2, log base 9 of n equals 4.5, and log base 9 of p equals negative 2.5. We're going to use these values to solve these logarithmic functions, right? So we're gonna kind of take this and break it apart into its parts, right? Because this is just 3 times m times p squared. So we can split that up into 3 different logs that are being added together. Right, this log base 9 of 3 plus log base 9 of m plus 2 times, because we had this exponent here, right? We pulled it out, 2 times log base 9 of p. And now that we have these values, right, we can just plug in what we know. Well, log base 9 of 3 is saying, well, 9 raised to the what power is 3. And I think I might have, hold on one second, guys. I did. So that's not supposed to be a 3. That's my bad, guys. This is actually supposed to say 0.5, right? Or 1/2. Because 9 raised to the 1/2 power is the same thing as the square root of 9, right? So the square root of 9 is 3. So we have this 0.5 here. Right? Then log base 9 of m, we just plug in the value here. And on log base 9 of p, we just plug in this value here, and we can just multiply and add that up. Right? And it's the same thing with 14 and 15, right? We're splitting it up based on its parts, right? This is n squared all over 9m, right? So this is n squared being divided by 9 and being divided by m, right? So there's 2 division problems, so we have to subtract twice, right? And once we have this all separated, well, we just plug in the values. We know log base 9 of n. We know log base 9 of 9. Well, that's just 9 raised to the 1 power is 9. And then log base 9 of m, we already know that. So we can just multiply this and get 9.2. Multiply and subtract it out. Number 15, same thing, right? M is just raised to the 1/2 power, so we can pull that outside. And we just plug in the values that we know. So let's keep going. Number 16 here. right? So here we're using what we know about logs to solve equations, right? And we got to think back of like what those strategies were. Like we had the warm-up problem where we went over 3 different ways to approach solving equations with logarithms. Right, so let's look at this first one. We know if we can get them to just be 1 log on each side, you can just chop the logs, right? So we're going to condense this because it's log base 4 of 16x minus log base 4 of x minus 5, right? And once we condense it, we can just chop the logs. So we can just say 16x over x minus 5 is just equal to 56. We would multiply that x minus 5 over and then distribute the 56. And we can say 16x is equal to 56x minus 280. And then once we solve that, right, we can subtract this 56 over. We get negative 40x equals negative 280. We just end up getting x equals 7. Right, 17 is pretty much the same strategy, right? We have a bunch of natural logs. If we condense them, we can drop the natural logs, right? So we just have this 8x plus 5 is going to be multiplied by 2, which is what we have here. And this 4 is going to be multiplied by 5x minus 1, which is what we have here. Since they're the same, they both have natural log, we can drop the natural log. We can distribute, so this becomes 16x plus 10 equals 20x minus 4, and then we can just solve, and we end up getting x equals 7 over 2. 18 is a little bit different because we don't have a logarithm on the other side. So what we can do is we can change it to our log form, or sorry, our exponential form, so that we can solve for it, right? Because natural log is just the same thing as log base e. So this is asking e raised to the 8th power is equal to 3x minus 5, which is exactly what we have here, right? Then we can add the 5 over and divide by 3, and these are all just values you can punch into your calculator, right? We can go e raised to the 8th power plus 5 and then divide all that by 3, and we end up getting 995.32. Number 19, we have a bunch of logs written here, right? We have 4 different logs. So we know when we see something like that where there's just logs on both sides, we know we're going to have to condense and try to drop the logs, right? So we can condense this. Remember, this 2 is going to become an exponent. So this becomes log base 3 of 4 times x squared. And we can condense this, and it becomes log base 3 of 80 divided by 2, which is just 40. We can drop the logs, say 4x squared equals 40. Divide by 4, we get x squared equals 10. And usually when we take the square root, what we have to remember is that it's plus or minus square root of 10. But because we have this log base 3 of x, we can't have a negative value inside of a logarithm. So it's just x equals positive square root of 10. Number 20, we have an exponential where our variable is in the exponent. And whenever we have a variable inside the exponent, we know we're going to have to change it to a logarithm to solve for it. So we take the base of 10 and we make that the base of our log. Whatever the exponential is equal to, we're going to put that inside of the log. And then the exponent is always by itself. Right, so we have this log base 10 of 140.57 is equal to 7 minus x, right? And we can just solve for x and just plug this value into our calculator. We can do log base 10. And remember, log base 10 is the same thing as if we just said log of 140.57. Right, whenever the base isn't written, we always just assume that it's 10. So in 21, we have pretty friendly numbers, right? We have 25 and 125, which was the same numbers we saw in those beginning problems, right? Because we know, well, 25 is the same thing as 5 squared, and 125 is the same thing as 5 cubed. So we can just kind of multiply those exponents together and make this 5 raised to the 2 times 4x plus 5, and 5 raised to the 3 times x minus 10. And now that they have the same base, right, all we have to do is set the exponents equal to each other. which here we can distribute and get 8x plus 10, and here we can get 3x minus 30. And when you solve that out, you end up getting x equals negative 8. Number 22, we see our variable in the exponent, so we know we're going to have to change it to a logarithm. And then once we have it in log form, right, it just becomes kind of an algebra problem, right? We subtract the 8, we divide by 3, and we end up getting x equals 3.495. Now, for number 23, there's two ways we can do this, right? Since we have the variable in the exponent, we know we can just change that to logarithm form, right? So log base 4 of 11 is equal to x plus 3. But what you can actually do too is we can take the log of both sides, right? Just like sometimes we like multiply both sides by 2 or something like that, right? To help out, what we can do is we can take the log of both sides, and then because this is just a 4, right, we can pull that x plus 3 out and then divide that log base 4. So it becomes log base 11 over log base 4, which we can just plug into our calculator, right? Then we can subtract by 3. But in either way you do it, though, you're going to get negative 1.270. All right, last page we'll try to get through pretty quick. We're talking about the compound interest problems. All right, so compound interest problems, we know we're going to be using one of two equations, right? This is when it gives us how many times it's being compounded, right? Because n is the number of times it's compounded. And then this is when it's compounding continuously. All right, so we got to be able to recognize when we need to use each. All right, so here it says compare the amount of money in two savings account after 15 years with the same initial investment of $15,290 and interest rate of 1.5% in each account if it's compounded semi-annually, right? And semi-annually just means that n is going to be equal to 2. So all we have to do is we have to plug in our values, right? The principal amount, this P, is going to be 15,290 because that's how much we're starting with, right? That's times 1 plus the rate, which is 1.5%. We can write that as 0.015, all divided by n, which is 2, raised to the n times t, which is 2, times the years, which is 15. Right, we plug all of that into our calculator, and we end up getting that it's $19,131.95. Now, what about if it's compounded continuously? Well, the values that we're plugging in don't really change. The only difference is instead of using this, right, we're using E, and then we're raising that to the R times T, right, R times T. So the rate is 0.015, and then the time is 15 years, right? But we can just, again, plug that into our calculator, and we get $19,148.01. So for the next one, we're talking about exponential growth and decay, right? This one says a computer virus is spreading through a network at a large corporation. It spreads continuously at a rate of 9% per day. The outbreak begins with 16 computers. So when we're talking about exponential growth or decay, we're using this equation, this A equals P times E raised to the RT. Right, and we want to know how many infected computers will there be after 15 days? Round to the nearest whole computer. And that's important, right? We're rounding to the nearest whole computer. So we want to know how many computers in a given time are going to be infected. Well, we know it's starting with 16, so the P is 16. That's going to be times E raised to the rate, which is 9% per day, right? So 0.09, times the number of days, which is 15. We plug all that into our calculator, we end up getting that 62 computers are going to be infected after 15 days. 27 asks, how many days will it take for the number of infected computers to reach 218? So it gave us our value for A, right? We want to know how long will it take to get 218. So we plug that in for A. We're still starting with 16 computers. We're just solving for T. right? But notice t is in the exponent here. So we know we're going to have to change it to a logarithm, right? So we can divide 16 over, we get 13.625 is equal to e raised to the 0.09t. And then we just have to change it to a logarithm, right? Log base e of that 13.625 is equal to 0.09t. We would divide the 0.09 over, and we end up getting t is equal to 29.02 days. And remember, log base e is the same thing as the natural log. So we could even say, right, t is equal to the natural log of 13.625 divided by 0.09. And this is what we could punch into our calculator, right? So number 28, the virus affects printers at will. It starts with 6 printers and spreads to 24 in 5 days. At what rate is the virus spreading? So this, it's asking for the rate, and we're going to write it as a percentage and round to the nearest hundredth. So it gave us that there's going to be 24, and it starts with 6. The time it takes to get to 24 is 5 days. So again, we have a variable in the exponent here. So we know we're going to have to change it to a logarithm, right? We can divide 6 over. 24 divided by 6 is 4. Then we can change it to a logarithm, right? Log base e of 4 is equal to 5 times r. We just divide that 5 over, and we end up getting that r is equal to 28%. 29. So an element decays at a half-life of 14.7 years. We start with 260 grams of this element. So 29 is saying how much will be remaining after 20 years, round to the nearest hundredth. So the first thing we have to do is, given the half-life, we have to find the rate, right? Because it doesn't give us the rate in any of the information. It gives us the time, but we want to know how much will be remaining after 20 years. Well, to find that, we have to know the rate. So first, we take the half-life, right? If we start with 260 grams, right, we know half of that is 130. And that's going to take 14.7 years. So again, we have an exponent, a variable in the exponent. So we're going to have to change it to a logarithm, right? So we can do 130 divided by 260. Well, that's just 1/2, right? Which makes sense, half-life. And then we're going to have to change it to log base e of 1/2 is equal to 14.7 r, which, when we solve for the rate, we end up getting negative 0.047. But again, that's an approximation. If we wanted an exact answer, right, we would have to use r is equal to log base e of 1/2 all over 14.7, right? We can plug that in if we wanted an exact answer to this equation here, but we can also just use this negative 0.047. All right, so now we want to know how much will be remaining after 20 years. So we know we're starting with 260. The rate we just solved for is negative 0.047, and the time is 20 years. Well, in 20 years, when we plug all that in, right, we end up getting 101.56 grams. Last one. How long will it take for the amount of element to decay to 144.21 grams? So this time it gave us the amount. Right? We want to know how long it will take. So we're solving for t. Well, we know the amount. We know the initial amount, right, 260. We know the rate. So we're just solving for t, and we know we're going to have to change it to a logarithm to do that. So we can do 144.21 divided by 260. That's this 0.554653, right? And then we can change that to a logarithm. So we're going to take the base here, e, log base e of this 0.554653 is equal to our exponent. Remember, we always want the exponent by itself. So negative 0.047t, we can just divide that over, and we end up getting t is just about 12.5 years. All right, I hope you guys found this helpful. If you have any more questions, feel free to reach out to us.